Hello everyone, welcome to Team 13's presentation on the project for ME555 Design Optimization. Our team members are Guru Prasad Sri Krishnan, Raghav Tripathi, Saransh Goel, Keshav Kulwal, Vishal Selvamani and Dev Khaudaria. In this project, we have chosen to analyze and optimize the design of an automotive braking system. The primary system we have chosen for this project is the basic automotive braking system, as shown on the screen. Its major functional parts include the brake calipers, pairs, rotors, and the master cylinder. Our system comprises three subsystems: the hydraulic system, brake control unit, and the rotor and pads. The rationale for the system level optimization problem was that these subsystems represent the key mechanical, electronic, and hydraulic components that collectively determine braking efficiency. Optimizing them individually while considering their interactions ensures a well balanced high performance braking system. As you can see on the screen, here are the main inputs and outputs of the three subsystems previously described. The outputs are fluid pressure for the first subsystem, the frequency of the ABS, the force on the calipers for the second subsystem, and finally the brake clamping force for the third subsystem. Further, you can also view the system flow diagram on the right, where the dashed line represents the system boundary, which indicates that the main output that we are finally focusing on is the braking efficiency. The shared variable is the brake swept area ABS between subsystems 2 and 3. The coupled output variable is the brake clamping force FPC from subsystem 3. Additionally, FCAL and FABS are the coupled outputs from subsystem 2. This can also be seen through the system boundary diagram.
Here you can see the system level optimization that we have done. We have also listed all the design variables we have considered and how we'll represent them in the MATLAB codes. Further, as marked in red, the auxiliary variables are the hydraulic pressure output as well as the brake force, which are used to decouple the system using IDS system level optimization. Here are the constraints we have considered for all the design variables we have used in this project. Additionally, we have included some intermediate constraints as well. These intermediate constraints are written in the negative null form, as this is the standardized format for writing and solving equations on MATLAB. The objective function of the first subsystem is to minimize the volume of the cylinder using the formula VMC equal to pi DMC square h by 4. This further feeds into a function f1 as shown in the second point. Further, we collectively minimize the frequency of ABS, the force on the calipers, and the brake temperature to give the function f2. These are the outputs from subsystem 2. Similarly, a function f3 is calculated taking into account the brake clamping force from subsystem 3. Finally, some weights are added to provide a final objective function. The decoupled system boundary has been shown. The auxiliary variable PF and FPC have been taken as the input of subsystem 2 and 3, which were previously coupled into the system. The design variables considered as well as the type of design variable and the subsystem they fall under are tabulated in the slide. It should be noted that after the system level optimization, ABS is the only shared input variable for second and third subsystem, and Y12 and Y23 are the auxiliary variables. The major trade-offs are also presented, such as the trade-off between the bore diameter and stroke length do not affect the fluid displacement. Further, the performance and safety should not be compromised while trying to improve compactness.
Continuing with the system level optimization model, we connect subsystems by linking variables. The brake swap area serves as a shared parameter between the brake control unit and rotors and pads. We use auxiliary variables like brake clamping force Y23 and hydraulic pressure output Y12 to decouple subsystems and eliminate direct coupling. In the system level idea formulation, this variable expand the design vector to include all local and auxiliary variables, enabling a seamless and optimized integration across the entire system. The objective function is a composite weighted sum of subsystem objectives to optimize the overall performance. Through the integrated design formulation IDF, the design variables specific to subsystems are retained, while the auxiliary variables hydraulic pressure output Y12 and brake clamping force Y23 are introduced to decouple direct interdependencies. Consistency constraints ensure these auxiliary variables align with the subsystem outputs, enabling system integration. Analytical modeling approach was utilized while mathematically modeling the system level optimization. This includes describing each subsystem by closed form analytical expression based on physical principles. Several assumptions were made to run the optimization efficiently and ensure computational feasibility, which are shown on the screen. These assumptions help simplify complex interaction while still providing valuable insights into the system behavior and performance during optimization. The major steps followed in mathematically modeling the system optimization can be seen on the screen. It begins by defining local and auxiliary design variables to manage interactions between subsystems. Objective functions are developed by normalizing and combining analytical expression for performance metrics. Constraints are established and the system level optimization is solved using the IDF method. Sensitivity analysis is conducted to evaluate parameter variations and the model is verified and validated against the real-time data to ensure accuracy.
Moving on to the optimization model for the system level, the algorithm that we have used is the individual disciplinary feasible formulation. IDF is computationally inexpensive and also allows each subsystem to be modeled with its appropriate analytical relationships. IDF also decoupled the interactions we had between the subsystems and introduced auxiliary variables y12 and y23. We have implemented this algorithm and code in MATLAB, which offers several advantages as shown. Coming on to the optimization results for 5 runs, we have tabulated the starting x0 values as well as the optimized values that we got in the first run of the IDF. There are notable differences in the initial and optimized values in all the design variables considered. The optimized objective value function comes to just above 14,000, which is the weighted sum of the individual objective functions. Similarly, a second run is performed, which provides us with further optimized values. We get similar values as we had received in the first run. However, the output pressure seems to have changed by 4 bars. The optimized objective value function gives the same output as the previous iteration. A third iteration of the IDF is performed, which again gives us a similar set of values for the design variables. The objective function is also very close to the previous run.
The fourth run of the IDF provided us with similar results as the previous runs. There is consistency observed in the objective function of the optimization model as well. The fifth and the final run of the IDF further sets in stone that the output remains the same for the rest of the optimized values, that all fall within the same range despite having slight variations in the pressure outputs. This slide highlights the constraint sensitivity analysis for our optimization model. Out of all the constraints, the following were identified as active constraints. Diameter and stroke length have the lower bound as their optimal value, whereas break swept area assume the upper bound as its optimal. We have adjusted these active constraints bound by scaling them up and down by 20% to assess their impact on design variables and functional value. The results along with percentage changes are detailed on this slide. From the parameter sensitivity analysis, we have found that the following parameters are critical for the system. Firstly, the mass of the rotor has been varied by 20%. The reason for choosing this is that it's related to the weight and inertia of the rotating components, which directly affect vehicle efficiency and handling. Brake pad friction, which is the friction between the brake pad and the rotor, μb, is the primary determinant of braking force output. A more efficient pad material requires less hydraulic force to achieve the same amount of braking. The variable A, ref, is varied to observe its impact on force transmission in the hydraulic subsystem and its interaction with system pressure. The brake pressure is an integral parameter in the model, and it is varied to analyze its effect on braking force across different conditions.
Our optimized solution from the system level optimization was compared with typical industry values. The results we obtained fall within the range of values reported from various sources, as illustrated in this table. On this slide, we are showing you the comparison of optimized values between the system and the subsystem. As you can see, most of the variables fall within 1% of the range of each other. Further, it can be noted that efficiency of venting patterns, EVP, has nearly become 20% of what it is in system level. Meanwhile, the rotor diameter has increased dramatically at the subsystem level with an initial wrong value of 0.5 meters, which was later corrected and optimized to just under 3.3 meters. Moving on to engineering interpretations of our optimization project, similar values were obtained for cylinder diameter and stroke length in the hydraulic subsystem, suggesting that minimal fluid volume is optimal for the system. Hence, weight reduction is also considered as critical. As for the rotors and pads, the lower bound of the brake pad emerges as the optimal value, indicating the maximum brake leverage usage. Our future work and model improvements include integrating dynamic brake torque curves for real-world driving conditions, allowing the use of non-constant friction values and utilizing cost models based on material selection, as well as more realistic manufacturing schemes. Thank you.